Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, Part 6 of these recorded sessions. Today, we'll be going over, for most of y'all, Chapter 6 and in general, organic reactions. So today we'll be going over the basics and, finally, reactions, right? So here's our agenda for today. Organic reactions, addition, substitution, elimination, redox, bonding, enthalpy, kinetics, thermodynamics, energy diagrams, and rate laws. So if you have any specific ones you wanna, specific topics you wanna go over, feel free to scroll over and find those titles on the page that we're working on. Okay, so let's get started with the first one. Okay, so first one, organic reaction. So this isn't gonna be specific reactions. This is going to be an overview of the, addition, substitution, things like that. So, but for each reaction, organic reaction, the process is the same. All addition reactions will go through this. All elimination will go through this, things like that. So first, let's start with addition. So with addition, you're always gonna, obviously it's gonna be added, right? But you're gonna have a pi bond break, and with that, two sigma forms, right? And let me get this out of the way. So that's what you'll see with addition reactions. And this is crucial because you'll see that, when we get to redox, it does the same thing, but it has to have this pi bond, it has to have the sigma form, right? And then we'll do practice this so it'll be more obvious. You'll see it better. Substitution, substitution. Did I spell that right? Yeah, okay. Substitution will have, obviously it's going to be a substituted, so one sigma breaks, and then forms again, right? And but this time it's on same atom, so it didn't move, it's still in the same atom, but it just got replaced, right? It got substituted. So all of these are kind of just like, common sense or whatever, but once you start mixing it up with the redox, it kind of gets confusing, or it kind of you miss that one thing and then you get it wrong, right? So these are essential bases, essential things to know. So elimination, you're losing something. So this one, two breaks, and pi forms, right? So easy as that. And you know, with addition and elimination, they're reversible. So let's add that. Um, Asterisk, reversible, reversible. And reversible because addition, elimination, those are just vice versa from each other, right? Basically. So now let's go to redox. And redox, I don't know if you've gone over it or you saw the, I don't know what video it was on, but anyways, we'll do a recap. Redox, we know it's between oxidation, reduction, things like that. So let's do reduction first. Reduction, you're gonna have, you're gonna be losing CZ bonds, gaining CH bonds or any hydrogen bonds, right? Oxidation, vice versa. CZ bonds, losing CH bonds. So you see how redox is not forming anything. It's not, taking away. It's not necessarily taking away pi bonds, or pi bonds, um, or double bonds, things like that. It's just as long as you add whatever Z heteroatom or H bonds, that's a redox, right? So now we have that. That's our basics. Let's do some examples and see if we can get these. Organic reactions. Okay, so let me give you a couple and then you guys can do them. So, oh, did I run out of room? Okay, Cl minus. So that's one of them. What kind of reaction is that? Do this one. And this one, what kind of reaction is this? And then this one's the same one, but the arrow's pointing the other way. Oops. So you guys probably already know what these are, but let's see. Okay, so a lot of different ways to ask this. And like two and three over here is kind of like forwards and backwards, right? And you guys can probably already tell what that is because we talked about it earlier. Oh, and this one's oh, it's okay. There you go. So take a second, take a minute, pause the video, and get back to me. Okay, so you guys should have gone for one, substitution, two, elimination, three, addition, right? And we did say addition, elimination are reversible, right? And as you can see here, reversible. So reversible, reverse, right? So kind of like a given, but let's just break it down with starting with the first one. Obviously, we have this, right? And what did we say about substitution? One sigma breaks, right? Sigma breaks, and then another forms on the same atom, right? For elimination, um, this one, elimination, we know two sigma breaks, right? So what's the other sigma bond that breaks? It's this hydrogen, right? So sigma here, sigma there, and then it makes that pi bond over here, right? So don't forget about the hydrogens, they are sigma bonds too, right? And then for addition, we have a pi here, and then we make two sigma bonds over here, right? So same thing. So don't forget about those. The trickiest is, H bonds. H bonds are sigma. So don't forget that, right? So just because you don't see them doesn't mean they're there, right? So that's it with organic reactions. Super simple. If someone says, "Oh, this is a substitution reaction," well, substitution reaction will go through this, right? One sigma breaks, another one forms on the same atom. Or this is an elimination. Elimination goes through this and turns into that, right? So you'll see a lot of, there's going to be a lot of specific reactions. They're going to have their individual names, like blah 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 reaction. But when it comes down to it, it's either going to be substitution, elimination, addition, right? And yeah, that's all you guys have for now. Nothing too crazy. And obviously, there's going to be like multiple steps. First step could be substitution. Second step could be elimination. Third step could be addition, right? So, but same concept, same basis. So, let's go to the next one. The next one. Now this is going to be a lot of just concept. So it's just going to be um, definition. So nothing too crazy, but just a recap. We have bonding, we have breaking and forming, right? So bond breaking is split into two. We have homolytic and heterolytic. Lytic, and you guys know that homolytic is going to be gonna be the same. So they're gonna be broken apart same. So something like this plus B, right? Heterolytic, something like this. One of them gets all of it plus B, right? And you notice here, let me change colors because it's gonna get too muddled. Um, this is probably the most important part. Homolytic, obviously, um, uncharged, charged, right? So that's all. That's the main difference between that. And you see here the radicals, things like that. Um, obviously, this is cations, anions, either ions. So that's what makes them different. But you guys get that. You guys don't have to worry about that. It's super obvious. Now with bond forming, um, bond forming is always gonna release energy. Releases energy, and you'll see later that when we go to kinetics and thermodynamics, and actually over here, it's gonna be you know exothermic because it releases energy, right? Exothermic, and then making breaking endothermic because you need energy, obviously, put in to break something, right? So I'm just gonna put here endo and then exo. Okay, so with forming also, obviously when you form something, it requires either two radicals or two charged species. So like these can go back and form AB. These two as well can reverse and go back to AB, right? So um, two radicals can form, or two ions, which is the homolytic and heterolytic pretty much, right? So not too crazy. Now, probably the bigger question here is the bond dissociation energy. Dissociation. So with this, we kind of already talked about it, but the definition is energy needed to homolytically cleave, right? Cleave bonds. Homolytically cleave bonds. And we already talked about how breaking is endothermic equals endo form exo. So that's all you need to know with that one, right? A lot of concept, and it makes sense. So it's all of these are kind of nothing too crazy, nothing too mind boggling, right? And now we go to bond strength, and hopefully I have enough room. Bond strength, obviously the stronger the bond, the stronger the dissociation energy, right? Because you're gonna need more energy put in to break something, right? Stronger the bond, stronger the I'm just gonna put dissociation energy, right? Dissociation energy, um, and vice versa, right? So that's it with that one. Or and then stronger the bond is also gonna be um, shorter bonds. Okay, just putting it out there. So nothing too crazy, just all concept stuff. These are pretty much the questions that you'll get asked. What happens with bond breaking? It's going to be endothermic. What happens in versus hydrogen bonds versus van der Waals? What's going to have the highest bond association energy? hydrogen bonds, they're gonna be stronger. So things like that. So, nothing too crazy, it's just all concepts. So that's all. So let's go on to our next one, which is probably more relevant, which is gonna be entropy. And I was deciding whether to add this to the kinetics and thermodynamics, but I didn't. Okay, so entropy, just since this isn't a full-on lecture, just kind of like getting to the point. Sum of broken plus sum of formed. Sum of formed. Okay, so nothing too crazy. So there's a little formula for enthalpy, and you know, just adding it over here. Positive H equals more energy needed to break, and then negative G, negative H, I mean, more energy released, released, right, in forming. So kind of like just vice versa. So, and that makes sense because um, just going by this formula, obviously, if it's positive, we're gonna have more energy, to break it. And actually, we'll do some examples here and kind of makes more sense, and we'll use a formula as well. So let's do that. So let's see. Calculate, and I think there's two questions. So calculate, but it's going to be the same um, format. Calculate the entropy, of course, for these two formulas here. CH3, 3CCl plus H2O. Going over here, CH3, 3COH, Cl. And they gave you the dissociation energies. So over here it's going to be 331, 498, 401, 431. So I hope we have room for the second one. Yes, we should. CH3, CH2, Br plus H2O. Going here. CH3, CH2OH plus HBr. So we have here 285, oops, 285, 498. This is a 9. 498, 343. Okay, yeah, that's 343 and 368. 368. Okay, so take a second, calculate both of the dissociation energies and come back to me. Okay, so you guys should have gone for the first one -3, and for the second one 22. So what we did is we just plugged it into the equation, right? Into this sum of broken plus minus sum of formed, right? So basically 331 plus 498 um, minus 401, 431, right? So this minus this, right? And for this one, you should have gone 829 minus 832. And that's how we got the -3, right? And you guys are probably asking, how do we know which one's the broken one and which one's the formed? Well, we just look at the arrow, right? This is the reactants and this is the product. So obviously this is the one that we broke, and to form these two, right? So that's all you need to know. Um, Reactants to products. And then same thing over here, minus again. For this one, you guys should have gone 783 minus 761, right? And that's where you got the 22. So not too crazy. And that's you're just plugging and chugging, right? Yeah. Okay. So let's start with enthalpy, and I did that separately because this is the only one you kind of really just. This is the only one out of the thermodynamics that you needed to actually calculate. Because the other ones are all trends and stuff like that, so it's easier to kind of figure it out. So let's go do those. Let's go do the. Let's go do those. Oh gosh. Okay. Kinetics and thermodynamics. So kinetics, obviously, the rates, um, thermodynamics, energies of reactants and stuff like that. So rate and then energies. So we know that, kind of an obvious one. And then we have equilibrium constant, which is going to be products over reactants, right? Over reactants, we have our Gibbs, which is the of products, free energy of the products minus the reactants. So simple enough, right? And then we have entropy. So entropy is kind of a combination of everything, right? So I'm gonna do this entropy. We have this Gibbs equals HO entropy minus T, right? So sweet. So now nothing too crazy. We know entropy is probably the most simple one. The more entropy it is, the more disorder, whatever, right? So now all we actually need is just all the trends, right? So let's start with entropy since that's the one we did before this. Entropy 0, 0, and let's do Gibbs here 0, 0, and then um let's do KEQ 1, 1. So now let's label them. If it's a positive H, it's going to be endo, negative H, exo. So super easy, right? And actually, let me change the color so it's not too orange. So what about G? G is kind of like, what happened there? G is kind of the same thing. With for these, you just follow for G, you just follow the arrow. It's gonna go to the reactants and the products, right? So it's kind of opposite. So going to the reactants, going to the products, um, and then let's see for equilibrium equilibrium constant, it's going to be directly the arrow, right? So this one's going to the products, this one's going to the reactants. So the products and then reactants. So as long as you know these, you're fine, you're good. You're not gonna. It's very rarely you're gonna get asked to actually calculate anything because especially for those of you guys planning on going to like professional school, things like that, you're not gonna have a calculator. So for all of these, even with the entropy over here for this formula, you can just, guesstimate if this is positive and temperature entropy is like positive, which one's the bigger positive is to make this negative. You know what I mean? So guesstimating things like that. But if you need an actual number, then obviously you're gonna need to, to calculate it. But um, once you get really used to it, it's good enough to know, oh, this one's going to the left, to the right. Um, especially since we're calculating for G here, you're gonna know exactly if it's gonna prefer the reactants or the products, right? So nothing too crazy. These these are probably the most annoying because especially with KEQ, don't confuse it with the zeros, right? This start off at one because this is greater than one or less than one, right? So the enthalpy and the Gibbs are the zeros. The equilibriums are zeros, right? But with equilibrium constant, it's one. So that's the only like tricky thing with that. So now, with that being said, let's do some examples. Kinetics and thermodynamics. And these are probably the most like you guys have seen these so many times from Gen Chem, and you'll see them again and again because kinetics and thermodynamics are one of those things that's like in every part of like science, right? There's always reactions going on, like even in biochem, especially in biochem, things like that. So you'll see these all the time. So now here, label um, the KEQ, G. So which ones are positive, negative, less than, greater than one, things like that, or endothermic. So here we go. These are gonna be really ugly, but you guys will get the point. Okay, okay. Now let me get you another one. What happens to entropy? So there's gonna be a reaction. One, two, three, four, five, six. So take a second, pause the video, and give me what you got. So I got for the first one, you guys should have gotten KEQ is gonna be less than one, and then G is gonna be greater than zero, and same with H, right? And this one is gonna be all equals. So KEQ equals one, equals zero, equals zero. KEQ, and then this is the G, this is the H, right? So that's all equilibrium, obviously, because it went back. And now over here, opposite, KQ is gonna be less than one, G is greater than, G is less than zero. Um, oh, did I just do that wrong? Okay. Wow. After all this time, I still get my signs confused. Okay. So KQ is greater than one, and G and H is gonna be less than zero, right? So nothing too crazy, and we know we got the enthalpy because we know this is gonna be exothermic, endothermic, right? Um, and with the G here is preferring the reactants. This one's preferring the products, right? So, and you can kind of just tell by the slopes of it, right? Um, this is more towards the reactants because it started off down here. This is more towards the products because it's super easy to get there. The activation energy is super low compared to this one super high. And then equilibrium constant is just going to, again, to the reactants, which is to the left, and then the products to the right, right? So now this second one is actually probably one of the best questions you guys will see because it's always confusing. But this one you guys should have gotten. Entropy decreases because um, once you close that up, we know that cyclics have less bonds, right? Because what's the formula? Cn H2n, right? CnH2n. But this one is CnH2n plus 2, so it has that two more bonds than cyclic. So obviously, if it has less bonds, it's gonna drop the entropy, so it's less disordered, right? So a lot of different ways to answer these or to ask these questions again, especially with these, you're not gonna get asked like all of these at one time. So what? This is how many questions already? Three, six, 9 questions with 3 figures, right? So definitely know your thing. Um, and this one's a good one too, the entropy. So things like that. When I had it, I didn't get asked to calculate every single thing, so you may be lucky. But if not, just use the formula we talked about and it's just plug and show, right? Okay, so let's move on to the next one. Our last topic for today. It's gonna be, and I think this is gonna be the most. Well, since we kind of already saw the diagrams and stuff, it shouldn't be that crazy. But this is gonna be energy diagrams, and rate laws. So for this one, it's really pretty simple. So obviously, the higher the concentration of whatever, the higher the rate, right? We know that from Gen Chem. Um, the higher the temperature, the higher the rate. I don't know why I bracketed these, but I guess the rate, right? Um, let's see, and that's with the energy diagrams. And now with rate laws, the higher the constant, the lower the activation energy, which means it's faster, right? And then vice versa. Constant, slower. And the rate law is actually rate plus K and just the reactants. So we just care about the reactants for the rates, right? So now the big thing with these two is, or actually, yeah, for both of them. So we know we have the Gibbs, the H, we have the equilibrium constant. Do not, do not determine rate because we said that kinetics is the rate, right? And thermodynamics is the energies because these are all thermodynamics. So these thermo only, right? You cannot mix your kinetics and thermodynamics. So listen carefully, especially if you're taking going to professional school or planning on taking the exam. Don't mix those up because that's like a lot of questions. That's a lot of questions, and those are easy questions to eliminate, to avoid, you know, to narrow down your answers. So thermo indicate um, direction, energy, right? So do not. So I don't even know how to start this. 2, 3, 4, 5. I'm gonna start all of that. Okay, so I don't know if I've emphasized it enough, but do not determine the rate. Okay, there's that. So only concentration and temperature determine rate. And let me color those in actually as well because I didn't emphasize that enough as well. So only these two determine rate, right? Determine rate. Okay, that's that. Okay, take a picture, take a screenshot. Okay, so now let's do some examples. Okay, So, and this is gonna we're gonna have a lot of examples because this is the funnest, um, or this kind of combines everything. So, it ties everything together. So, energy diagram and rate laws. Okay, so let's see. How many transition states are in here? Okay, so let's do here. What is the rate equation of this? H2O. I'm gonna have room. Shit. OH2 plus there. Okay, I think I okay. OH plus HCl. So what is the rate equation, right? Um, and also for this one, using the same equation, and let me do this. I'll have this A, this B, this C, and this D. For these three, which has the highest energy? Highest energy between A, B, C, or D. So A, B, C, D. And then last one, 4. Um, calculate, and we're gonna have room. Calculate EA for C to B. Okay, so and we have this. This is gonna be this is not gonna be drawn to scale. So look, I'm gonna try my best. Okay, so this is A, this is B, this is C. So and we're given the activation energy. So EA for A to B is plus 10, for B to C is plus 4. Okay, there's still room. And for H, they're giving us for A to B as well. Is this a mess? Okay, don't let me know. B to C is minus 5. Okay, so, but we want the EA for C to B. Okay, pause the video because you're gonna need it because this got messy, and tell me what you got. So first, I'm gonna do different colors for each of these so it doesn't get too confusing. How many transition states? We know these are transition states, right? So we have 2 transition states. What if I told you how many intermediate states? What do you guys get for intermediates? So we said TS over here, TS. For intermediates, we have 1 intermediate. So, and this is our reactants and this is our products. So that's how you look at those. Super simple. So now what is the rate equation? We know, we talked about the rate law. So we know the rate law is gonna be K parentheses reactants, concentration of reactants, right? So obviously it's just going to be, um, let me put it here. Rate equals K, and I'm just going to draw it here, just to make it simple. That's it. So rate K of whatever this is, whatever reactant is, right? So you can even have it as CH3, CH, CH, Cl, CH3 or something, right? So, and actually, let me do that here. CH3, CH, Cl, CH3. So you can use that as well. So, and that's it. You got this whole equation, but all we care about for the rate law is the reactants because that's what we're starting with, right? So nothing too crazy. So now let's go to which one has the highest energy? A, the reactant, B, intermediate, C, intermediate, or D, product. So you guys should have gone this one, B, right? Or I guess I should do it here. B, because um it has the most charges, right? Most charge. So, and we know the more charge it is, even with resonance, all that, it's unstable, so it's gonna have the highest energy, right? Unstable. Things like that. So you didn't really have to, do any tricks or go do all these crazy things with it, find out all the energies, the formulas or whatever. You just needed to know that if it's unstable, if it has all those charges, it's gonna have the highest energy because we know higher the energy, more unstable, right? So that's all you need to connect. With now four is easier than you think. Let's do blue. So for CB, you guys should have gone +9. Why? Because here the activation from A to B here is 10, and then B to C is 4, right? And then that's for the activation energy. For the enthalpy from A to B over here is 8, and B to C. And again, I said this was out of scale, very very out of scale. Um, but basically, you just needed to add B's up, right? So let's see, I have my notes here. Um, so 10. So if it was from C to B, right? C to B, you would have added those together. So you would have added the 5 plus 4 because the enthalpy is this, right? So what is it? The enthalpy BC is 5, and then the activation energy is 4. So 5 plus 4 is 9. So that whole thing, that whole activation energy, right? So basically for this one is you had to know what the activation energy was and where to label it, and same thing with the enthalpy. So knowing that this over here is the activation energy, um, this over here is activation energy, and the you know the intermediate and the products, the intermediate and the reactants, those are the enthalpies. So that's all you needed to know, right? So, and with that being said, that's all for today. That's all we have. And again, these are what we covered. Hopefully that helped. Um, and yeah, hopefully you guys come back and watch the other videos. There's more to come. So I'll see you guys later. You guys have a good day. Okay. Huh? Stop the video.